Hello again, this is Mr. Smith with Reading Quiz 15. This reading quiz is about parametric equations and their derivatives. We did a little bit of this in the lab, and so part of this reading quiz reinforces a lot of what we did in the lab. So let's take a look. So first question relating to calculus is, how do you find a derivative for a parametric equation? Well, in the lab you discovered what happens when the two parts of a parametric equation are both linear, and the parts would have an x component and a y component. And what we discovered is the slope of this parametric equation is the rate of change of y over time over the rate of change of x over time. And that's very similar to what we already know the formula is for slope, dy dx. In our case, since we are dealing with this third parameter, time, our new formula for the derivative of a parametric equation would be dy dt over dx dt, as long as dx dt is not 0. As the Stewart book puts it, if we think of a parametric curve as being traced out by a moving particle, then dy dt represents the vertical velocity of the particle, and dx dt represents the horizontal velocity of the particle. And so dy dx represents what the slope of the tangent is involving those ratios of those two velocities. Tangents. We covered tangents when we did implicit derivatives. And we had two types of tangents, the horizontal tangent and the vertical tangent. And if you remember, the horizontal tangent was when our numerator was equal to 0. In our case here, if you look back at the formula for the derivative of a parametric equation, that would be where dy dt is equal to 0, assuming that dx dt is not 0. That should make sense. If dy dt is equal to 0, that means we don't have any movement in the y direction. Similarly, the curve has a vertical tangent whenever dx dt is equal to 0, assuming dy dt is not 0. And looking back to the previous slide, we can see that's where our denominator is equal to 0. And that's where we have a vertical tangent. So just as an example here, I say consider the parametric equation x of t is equal to cosine of t, y of t is equal to sine of t. And this particular equation will have a vertical tangent whenever dx dt is equal to 0. That's negative sine of t. And if you recall your trigonometry, sine of t is equal to 0 whenever t is equal to 0. And that'll be at this point that I'm indicating here, which is at 1, 0. And that's where our dx dt is equal to 0. We have a vertical tangent there. We have horizontal tangents whenever cosine of t is equal to 0. That's when dy dt is equal to 0, and we have no y movement. And that occurs at pi over 2, which will be the corresponding point of 0, 1. So basically the idea is when you want to find vertical tangents, you set your dx dt equal to 0 and make sure that your dy dt is not 0. And then horizontal tangents will be wherever dy dt is 0 and dx dt is not 0. So relating all this to kinematics terms, remember that speed is the absolute value of velocity. If you remember from a while back when you guys did vectors, you learned that the absolute value, essentially, or the magnitude of a vector, is related to the distance formula. In our case, the absolute value of a vector is the magnitude or length of the vector. And what we're finding when we're finding the absolute value of the vector b of t is we're finding the speed. All right, and in our case, the speed will just be the square root of each component. In this case, the component of our x velocity, which would be dx dt, and the component of our y velocity, which is dy dt. All right, and I have a little triangle to demonstrate why and how this relates to the distance formula. In our triangle, the dx dt represents one leg of the triangle, and dy dt represents a second leg of the triangle. And so the length of the vector that connects the starting point to our ending point would be square root of dx dt squared plus dy dt squared. Secondly, the statement that a particle is at its leftmost or rightmost point refers to finding the absolute maximum or absolute value minimum of the x parametric component. Okay, so we will do a candidates test on our x component to find left and rightmost points. Similarly, the statement that a particle is at its highest or lowest point refers to finding the absolute max or absolute minimum of the y part. Okay, so x means left and right, y means high or low. The second derivative is a little bit more of a complicated subject, and we'll probably need some time in class to talk about this. What if we want to find the second derivative of our original derivative with respect to x? So if you'll remember, the formula for dy dx was dy dt over dx dt. In other words, the ratio of the rate of change of the function with respect to time versus the input with respect to time. Well, if we're finding a second derivative, we need to find the derivative of the derivative with respect to time. And all we're doing right here is, in place of y, we're putting in dy dx because we're finding the derivative of the derivative. So the dy dx takes the part of y here. The reason why we divide by an extra dx dt is because of the formula above. We are dividing the rate of change of the function, which in our case is the derivative itself, over the rate of change of the input. And that's how parametric derivatives work. So we're always going to have that extra dx dt factor in our denominator when we're dealing with a second derivative. Another way of putting that is we're dividing by the dx dt because of the fact that we're trying to find the derivative with respect to x, not to t. We already have the derivative with respect to t. That's the upmost part. But if we want to fix this and find the derivative with respect to x, then we divide by that extra dx dt. So example 1, I will lead you through one example here. If we want to talk about the others in class, we certainly have time to do that. So first part, a particle moves in the xy plane so that the position of the particle at any time is given by x of t is equal to t squared plus 2t, and y of t is t squared minus 2t plus 3. Part A, find the velocity vector for the particle in terms of t, and find the speed of the particle at time t equal to 0. So velocity vector will have two components. It'll have an x component, just like our parametric equations, and a y component by finding the derivatives of each of those pieces. In our case, the derivative of the x of t part is 2t plus 2, and the y of t part's derivative is 2t minus 2. And so we put that into our vector form. The speed, all right, if we remember from a couple slides back, the speed is found by taking the square root of dx dt squared plus dy dt squared. In our case, we already have dx dt, that is 2t plus 2. We plug in 0 into our equation. Similarly, we do the same for y of t. We find y prime of 0. In that case, we get negative 2. So squaring both of them and summing them, we get square root of 8. Speed is a pretty easy formula to use in this case, if you just remember that it's related to our x and y velocity components. Same problem, except in part B, we want to find dy dx in terms of t and find that limit as t goes to infinity of dy dx. So with our formula, we have dy dx is equal to dy dt over dx dt. We put them over each other. That's pretty simple. And then evaluating the limit as t goes to infinity of that, we get 2. What does that mean? That means as time goes on, our slope of our parametric equation will level off to 2 in the long run. Same problem, but here we've got find each value of t at which the line tangent to the path of the particle is horizontal, or explain why none exists. If we scroll back a couple of slides, we remember that we have a horizontal tangent when dy dt is equal to 0, assuming dx dt is not 0. So we need to find dy dt, which in our case is 2t minus 2, and we need to find out when that function is equal to 0, which would be at time 1. So in order to double check, we make sure that x prime of 1 is not 0. We know that dx dt from a previous slide was 2t plus 2, which is not 0 at t is equal to 1. And so we can conclude that we have a horizontal tangent line at t is equal to 1. If we wanted to find the point where that we have our horizontal tangent line, we would just plug that t is equal to 1 back into our equations for x and y. Part D, find each value t at which the line tangent to the path of the particle is vertical, or explain why none exists. Here again, we need where x prime of t is equal to 0. Since x prime of t is equal to 2t plus 2, that occurs when t is equal to negative 1. Y prime is not equal to 0 at t is equal to negative 1, so that's where we have a tangent to the path that's vertical. So again, vertical dx dt is equal to 0, horizontal dy dt is equal to 0. Part E, find the second derivative with respect to x. We saw from a previous slide that dy dx is equal to 2t minus 2 over 2t plus 2. In other words, that dy dt over dx dt. So again, note that the derivative of a parametric function is always dy dx is dy dt over dx dt. And the second derivative is just the derivative of the first. So if we're finding the second derivative, we need to find the derivative of the derivative with respect to time. So if you notice on this screen, what I did on the top is I found the derivative with respect to time of dy dx. dy dx is 2t minus 2 over 2t plus 2. So we're going to use the quotient rule on this. And remember the quotient rule, low d high minus high d low over low low. In this case, we get 2t plus 2 times 2 minus 2t minus 2 times 2 over 2t plus 2 squared. That's the top part. We are taking the derivative of a parametric equation. So what we've done is we've taken care of the derivative with respect to time. But just like any other parametric derivative, we need to find the derivative of x with respect to time. And that'll go on the bottom. That's why we have an extra 2t plus 2. Simplifying all of this, we end up with 8 over 2t plus 2 cubed. Notice the extra dx dt on the bottom. And notice that we have a cubed on the bottom. That's oftentimes what we'll see since we're dealing with quotient rule, oftentimes in conjunction with an extra dx dt. We'll do some more examples of these in class, and we'll talk through it a little bit more.